Hi, today I'm going to talk about some optimization and root finding function or package in R. So first of all, you need to, for all these package, you need to have the latest version for R to install this package. So here I have, first of all, I have a package for the linear programming. So let me run this code and show you the result, and then I will explain what it's actually doing. So you can see that you have the solution and then the optimum here. So for any optimization function problem, you have an objective function. So for here, basically you have your this is a vector form, but basically what you are doing here is that you want to so here this is a maximize question. So basically you are saying that I want to maximize a function with 2 times let's say x1 plus 4 times x2 plus 3 times x4. So this is your objective function. So you put all your coefficient in a vector form, and now you also have a constraint. So if you are familiar with the standard form for to rewrite a constraint, then after you rewrite your constraint, if there's some some special request in your constraint, you need to convert into a standard format, and then you bring the coefficient into a matrix. So basically the matrix something like this. So the first, so for this linear system, you have so your first constraint, and also with this the direction and your the right hand side. So basically for the first row, you have 3 times x1 plus 4x2 2x3, that is less or equal than 60. Similar for the second row and the third row. So basically if you are familiar with math, this is a matrix form for your constraint. It must from a standard format of your constraint. So you have your coefficient, the constraint, the sign for the constraint, and then your boundary for the constraint, and then your and then you specify that this is a maximization problem, and then you run this code. This will give you the solution for x1, x2, x3. So if you bring we can if you put these number here, 0 and 6.66 and then 16.66. So if you calculate this number, this will equal to your optimum here. So this will give you the optimal solution, the maximization of this function here, of your objective function based on the constraint you set here. So there's a package here in R to solve a linear programming problem. Okay, so for a one-dimensional parameter problem, you can also use the optimize function in R, which is a very basic function in R. So here I'm using I'm recently reading a book, and then the books there are a lot of examples in it. So the book talks about this. I think it's called linear joins function for a molecular dynamic problem. So to optimize that, there are some constant here. So I think those are predefined, or you can alter later. So the problem here is the objective function here is to optimize this function to find the minimum. To minimize this function based on one parameter r. I believe it's something related to a temperature or something like that. So first of all, to use the optimize function, you need to put your objective function into a function form. Then you just call the optimization and then and then tell your system or tell your machine where the location to look for these to look for the minimum. So one of the drawback is that you need to define a search area, a search boundary for your search to find the minimum. If your minimum is not included in your search area, then your answer can be biased. So if you already know, so this is like a textbook example. So let me run this function. So the function is your objective function, and then call them optimize, and then print the result. So if you plug this number into R, since you already have the sigma and the epsilon, and then your calculation will give you your minimum of this one. Okay, so you have so if you have a constraint, then you can use this linear programming tools here. And then if you have a one-dimensional, and then you can always, the optimize function is very useful and very powerful in R. So you can always build your own programming and then use the optimize function to find your extreme point. So I think we all know that the basic logic to find the optimization is to or a mathematical way is to find a first order derivative, set it to 0, and that is your convex or concave point. And then you can also check for the second derivative or the Hessian matrix to decide whether this is a maximized point or a minimum. So in that case, first of all you need to know the derivative of your objective function. However, so given that if you know the derivative, you can just find the root of your first order derivative. So that means a root finding package or algorithm is also important in your optimization problem. So here I'm going to introduce two root finding function here. So first of all, it's called root1. So similar to the previous example, you also need to write your objective function in a function format, and you also need to define your search area. So here you can see that for this function you have your root at 1.6. So if you put 1.6 into this function, and then the result should be 0. 1.6094. Okay, very close to 0. Since this iteration, so you also have to set, you need to set your search area and your tolerance. The tolerance is that the difference between n and n minus 1 iteration. So if the difference between two iterations is less than your tolerance, then the algorithms will stop, and then the point you find at the last iteration will be your optimization point. So however, for this function, I believe there's a drawback, is that well, first of all, you need to define your search area. So that could be your problem if your minimum is not within your search area. The second drawback for this function is that if your function is not having a different sign, let's say go out if a line is if a line past the y-axis, that means that means your line, the value of your line will have different signs between your at the different search area in of your minimum. Then this algorithm will not find the minimum. So for example, if you have a quadratic function where the minimum, where the domain for that the y value is always positive, although there is a minimum for a function, this this package will not find the minimum since your function did not cross the zero line. That means it will never have an opposite sign for your function. So this function will not find the minimum, or sorry, will not find the minimum by finding the root of your by finding the root of your first order derivative. So that can also be another drawback for this function. Okay, so here I have another root finding function for a polynomial. So you also need to write your coefficient in a vector form. So basically, I'm just rewriting this one. So that means the quadratic terms has a coefficient 0, and this plus 1 multiplied by x to the cubic. So so now you have your coefficient in the vector form, and then you can find your there are 3 roots for this polynomial function. So you can see that you have 3 roots, and then 2 of them are complex root, and then you also have a real root. So this function polyroot will help you to find the root for a polynomial. So here are some functions that I was recently reading a book. So here are some functions or a package to help you to look for optimization problem, or also root finding algorithm. Basically, it's also an optimization problem. So thank you very much, and let me know if you have any questions.